In this video, we describe sampling, noting that a random sample can be used to produce an unbiased estimate of a population statistic. We note that the precision of estimates based on a sample is related to the statistic itself, how the sample was drawn, and the size of the sample used to calculate the statistic. If we wanted to know about a population characteristic, say, what proportion of people have no religion, we could just ask everyone. This is the approach used in traditional censuses. In fact, the last census estimated that 27% of those who gave an answer in England and Wales reported having no religion. However, most surveys take advantage of the power of sampling to estimate population characteristics. At the heart of drawing a sample that can produce representative estimates for the population in a predictable way is the idea of drawing random samples in which it's possible to work out the probability of each case being included in the sample. Samples like this are known as probability samples. If we chose an entirely random sample, we would expect it to be unbiased. What does that mean? It means that if we take a reasonably sized sample, we might get the same proportion of people without a religion as in the population at large. However, because the sample members are drawn at random, we might not. It might be higher, it might be lower, but overall it's much more likely to be near the true population figure than far away from it. In fact, if we were to take all the possible samples, we would find that the average of all estimates would be the same as the population value, with estimates becoming increasingly unlikely the further they are from the mean. This principle is at the heart of survey statistics. Samples that are selected on some other basis, such as convenience, do not adhere to these rules, and survey statistics methods will not usually be appropriate. However, if the sample is based on a probability method, some designs may still introduce a bias for reasons of practicality or preference. Bias may also arise because those who responded were different in some way from those who did not. Where this is so, a statistical fix called weighting might be necessary. This makes underrepresented groups count more and overrepresented groups count less. Weights are often provided in the data to enable this. While a sample might give an unbiased estimate, it might also be too imprecise to be useful. Let's say that we produced a random sample from which we estimate that 59% of residents in England and Wales say they are Christian. We can use the known characteristics of random samples to estimate how accurate that percentage is. The precision of the percentage depends on the percentage itself and the size of the sample used to calculate that percentage. With a sample size of 10,000, we can be 95% confident that the true value of the percentage of Christians in the population is somewhere between 58% and 60%. That's an estimate that's precise enough for most purposes. That range is known as the 95% confidence interval. It's defined as just short of two measures called the standard error each side of the percentage. However, if we had obtained the same percentage using a sample of just 100 cases, we could only be 95% confident that the true population value was somewhere between 49 and 69%. That's a range of 20 percentage points, which is too wide for most purposes. Generally, larger samples result in more precise estimates. The statistic itself also affects things. If we calculated from a sample with 1,000 cases that no one or everyone in the sample had a characteristic, we would be led to believe that there is no variation, and the 95% confidence interval shrinks to nothing. There's much more variation if half the cases report having a characteristic. The 95% confidence interval would be between 47 and 53%. The nearer you get to 50%, the more the estimate varies. It's worth knowing that the precision of the sample can also be affected by the sample design. So if a sample design only samples from certain geographical areas to facilitate fieldwork, for example, a process known as clustering, the estimates produced will be less precise than if the sample had been taken purely at random. Intentionally splitting the population into groups and sampling from each of them to ensure that they are all properly represented, on the other hand, can make the samples slightly more precise.